Welcome! In this lesson, we will build an intuitive picture of active fold and thrust belts around the world. We will look at 5 case studies: the Zagros Mountains, the Himalayan foreland, the Sub-Andes, the Tian Shan, and Western Taiwan. Along the way, we will connect structure, rivers, climate, and earthquakes to understand how folds grow and how landscapes respond. Before the world tour, let's anchor the ideas with a simple schematic. Folds are bends in layered rocks. Anticlines are arch-shaped crests. Synclines are bowl-shaped troughs. In many belts, layers detach and glide along a weak horizon called a detachment or décollement. Compression from plate convergence builds these ripples through time. First stop, the Zagros of Iran and Iraq. Think long, parallel anticline ridges upheld by resistant limestone. Many folds ride above a slippery salt or shale detachment, so they can grow without a surface-breaking fault. Rivers like the Karun and Des cut straight through the ridges, making water gaps. Some abandoned passes are wind gaps. Modern data show active growth, about 1.5 millimeters per year on a basement fault at the front, and roughly another 1 to 2 millimeters per year taken up by detachment folding in the foothills. Earthquakes occur on blind faults, warping the surface and feeding the folds. Next, the Himalayan foreland, also called the Siwalik Hills. The main frontal thrust uplifts fault propagation, folds that verge south. Here is a single ridge with a steep front and a gentler back limb, a classic fault bend fold geometry. Terrace stairs and a river cutting through the ridge let us measure uplift, with shortening around 21 millimeters per year in places. Great earthquakes can push the fold several meters in one event, so hazards extend beyond a single fault line. Now the Sub-Andes on the humid east flank of the Andes. Thin-skinned folding above weak layers builds a shingled stack of anticlines. Dense rainforest hides the structure, but rivers and subsurface data reveal active growth. Synclines act like gutters. Longitudinal rivers run along strike before finding a pass across a ridge. Gigantic megafans spread sediment into the foreland, shortening rates of a few to 8 millimeters per year, with uplift along active fronts of around 1 to 2 millimeters per year. The Tian Shan is an intercontinental mountain system with active folding in its forelands and basins. Arid to semi-arid climate preserves sharp wind gaps and fold noses. Some anticlines laterally propagate, linking segments over time and capturing streams. Uplift rates on active folds of about 1 to 3 millimeters per year, with distributed convergence of 5 to 10 millimeters per year across the range. Some shallow detachments creep slowly between earthquakes, so folding can be partly aseismic. Finally, Western Taiwan, where active detachment folds underlie densely populated plains. A tight anticline grows above a creeping backthrust, producing steady warping recorded by terraces and geodesy. The 1999 Chi earthquake showed how a single event can instantly add meters of relief as a flexural scarp. Uplift of a few millimeters per year in the middle of some folds matches steady creep. Elsewhere, segments lock and release in earthquakes. Hazard awareness focuses on both scarps and warping. To wrap up, across these belts we see common threads. Layered rocks fold above detachments. Rivers record growth through water gaps, wind gaps, and tilted terraces. Rates range from millimeters per year to centimeters per year in shortening, and hazards include earthquakes, creeping warps, and landslides. Integrating structure, geomorphology, geodesy, and dating lets us decode how folds evolve. Thanks for exploring the world's active fold and thrust belts. Keep an eye on rivers and ridges. They are the landscape's ledger of ongoing tectonics.